Okay, cool. So I welcome you all to the third week of live sessions, Principles of Downstream Techniques in Bioprocess. And we'll start right away. Before that, I have to mention that in week one, I think, question number 7, we did a pie chart or analysis of percentage of expenditure in for manpower, raw materials, quality control, and etc. I think. So in that, somebody actually pointed out it. I think it was Burja Narang. I'm not sure. I should check. Uh, they asked me if he or she asked me if I have to take 25% of the whole or the remaining 50. I had made a mistake in reading the question. So please do check the description or the comment that I have posted for week one. So let's proceed with today's lecture. Yeah. So the topics covered this week are continuation of cell breakage and two lectures on solid liquid separation. Let's look into the first question. I think there's an overlap of topics. I mean, those cover the concepts or formulae discussed in previous week are also being used, but the concept is the same. We are still doing cell breakage. Okay. As usual, we'll take 2 minutes to take in the question, try to answer it, and then you can send in the answers to me through chat. All right. So I'm not sure if my audio is great. So I would like it if you can send me any comments in chat. And anytime the presentation is not visible to you, please let me know. Okay. In a bead mill, 65% of the intracellular enzymes are released in 5 hours. How long will it take to release 75% of them? Assume first order release process. For those who joined recently, we're looking into the first question for the week. In a bead mill, 65% of the intracellular enzymes are released in 5 hours. How long will it take to release 75% of them? Those of you who don't remember the formula, and if I'm making some mistakes, please point out. And if I proceed with the same thing, just point it out to me. Even I mean, make your point clear so that I take a moment to review what I've written or said. Okay. Anybody? George, Rishikesh, Sriram, Urja? Okay, let me help you a little. So, in the wheat mill, 65% of the intracellular enzymes are released in 5 hours. So, case 1, what do we have? 65%. So, 0.65 of C naught. Can I take it like that? C is 0.65 C naught, where C naught is the total concentration of enzymes, intracellular enzymes present within the cells, is equal to C naught into 1 minus e power minus kT, where T is time and K is the release constant. So can I cancel these? So 0.65 is equal to 1 minus e power minus kt, or e power minus kt is equal to 1 minus 0.65, correct, which is 0.35, right? So ln of e power minus kt is equal to ln of 0.35. Or if you want to do comfortable with ln, right? So minus kt is equal to, what's ln of 0.35 is minus 1.0498, and t we know is 5 hours, right? So k is equal to 1.0498 divided by 5 is equal to 0.2099. Maybe I can keep it as 0.21, or zero point 0.2 is fine. Our inverse, is that right? Now the second part is, what is the time required for 75% of it to get deactivated? So what will that be? 0.75 into C naught is equal to C naught into 1 minus e power minus k is 0.2 R inverse into time is, so that's what we need to find in hours, correct? So once again I can cancel these. 1 minus e power minus 0.2 t is equal to 0.75, or 0.25 is equal to e power minus 0.2 t. Again ln of 0.25 is equal to minus 0.2 t. Ln of 0.25 is minus 1.386 is equal to minus 0.2 t. T is equal to 1.386 divided by 0.2, which gives me 6.93 hours. Is that right? What do you guys think? If you're getting some other answer, please let me know. Any response? Okay, people are still joining, I guess. Hmm. Thank you, Sagar Jyoti. I was just wondering if I did log, will it differ? I mean, since you're using log on both sides, and if you do the same on the other case also, you are ending up with 6.68 hours, I think. Lon is good enough. Just wanted to make sure I wasn't making any errors. All right, shall we move on to second question? So let's write the answer here. 6.93 hours. Question 2. Protein deactivation as a function of temperature follows a first order kinetics with activation energy of 2.5 kilocalories per mole. The protein release from inside the cells rate constant follows an Arrhenius relation such as the constant term is zero point 0.1. All they are trying to tell us here that Arrhenius constant is 1. Here if the temperature is 50 degrees Celsius, what is the release rate constant at this temperature? Take a moment to answer this. If you want, I can write the formula here. This is the Arrhenius equation, right? So deactivation energy, instead of activation here you will have deactivation. So ED is 2.5 kilocalories per mole. The protein released from the inside is follows an Arrhenius reaction such that A is equal to zero point 0.1. Temperature is equal to 273 plus 50. This is equal to 323, is it? Yeah, Kelvin. So the units of temperature and energy will depend on what R we are going to use. So since it's in degrees Celsius, does anybody have an answer? Just substitute these values. What is the release rate constant at this temperature? They're just asking for K. K is equal to zero point 0.1 into e power minus 2.5. Let's do one thing. Great, Sagar Jyoti. Is it Kelvin here? Okay, I thought the units was in Kelvin. Thank you, Sagar. So I substitute 323 here then instead of 50. Then I arrive at 0.1 into e power 3.899, which is 0.02. So into 0.1 would be 0.002. Great. Thank you, Sagar. So the units is in Kelvin. Question 3. You are operating a homogenizer at an upstream pressure of 300 bar. You connect two more homogenizers of same capacity in parallel to it, and the upstream pressure now is 190 bar. What is the increase in capacity in percentage after adding two units? Assume other parameters to be same and capacity is proportional to the upstream pressure. So let me put out a diagram for you. You're operating a homogenizer. Let's assume this is the homogenizer. So initially the upstream pressure is 300 bar, and then you're adding two more homogenizers in parallel. In parallel. Now the pressure has changed to 190 bar. So what is the increase in capacity in percentage after adding two units? Assume other parameters to be the same, and the capacity is proportional to upstream pressure. So does anybody have an answer, or shall I go ahead and solve this? Okay, I'm taking that as a go ahead. So we know that the throughput, the output is proportional to the pressure. So there's a proportionality constant here, but when we are comparing two sequence scenarios, you can omit that part. So Q1 by Q2 is equal to P1 by P2, right? So since I'm going to have Q2 as my unknown, I'd like to flip this equation as Q2 by Q1 is equal to P2 by P1. And I know that P2 by P1 is, second pressure is 190 into 3, because we have 3 homogenizers here, right? Divided by the first pressure is, upstream pressure in the first case is 300. Is that okay? So I can cancel 3 here and 3 here, so that leaves 1 by 100. So moving 2 decimals, I would have 1.9. So Q2 is 1.9 times of Q1. So what does that mean? It is 1 plus 0.9 Q1, or there is a 0.9 times increase. In percentage, since they've asked the answer in percentage, that will be 90% increase. Agreed? If something was 3 or 2, you would have said 200% increase or 300% increase. Twice. I'm sorry. If it was 2, it is twice. So which is a 100% increase. So since this is 1.9, if you omit the first 100, it will be a 90% increase because it's an increase. Right? Sounds fine? So we have our answer as 90%. Okay. Shall I move to the next question? Question 5. Solids A and B have compressibility factors of 0.8 and zero point 0.3 respectively, but the ease of filtration is the same in both the cases at the same pressure. If the pressure of filtration is doubled, which one will filter faster? Solids A and B have compressibility factors 0.8 for A and 0.3 for B, but the ease of filtration is the same. Is that right? Yeah, let's take a minute. The ease of filtration is the same in both cases, or the ease as in the resistance is the same, so the ease of filtration is also same. Correct? So if I were to equate like this, and if this was constant, if this part is constant, then I can say delta PA whole power SA is equal to delta PB whole power SB, right? Which means PA here is, let's just call it PA. Delta PA power 0.8 is equal to PB power 0.3, whatever the value of pressure may be. Now, if the pressure of filtration is doubled, which one will filter faster? So, if 2PA power 0.8, right? This is case 1. 2PA power 0.8 is 2 power 0.8 into PA power 0.8, which is equal to, let's see, 2 power 0.8 is 1.741. I'm just going to take it as 1.74 for now. 1.74. PA power 0.8 is PB power 0.3. So I'm going to keep it as PB power 0.3. Case 2. 2 times PB whole power 0.3 is equal to 2 power 0.3 into PB power 0.3. I'm going to keep PB power 0.3 as the same and just calculate 2 power 0.3, which is 1.23 PB whole power 0.3. So the resistance is coming from this factor, right? The compressibility factor. If the compressibility factor S is 0, it is incompressible cake. So the resistance is lower. When S is 1, there is this factor contributing. Correct? And it increases the pressure. PA power 0.8, I am equating this with PB power 0.3 for the sake of clarity here, so that I can compare these two components here, Sriram. It is PA till here, but I have used this particular equation to substitute here. So I have PB on both sides. So you know that resistance in 2 is smaller, lesser than resistance in 1, correct? The pressure dependence. So what does that mean? Filtration will happen faster in B. Does that make sense to everybody? So initially when the compressibility factors are 0.8 and 0.3, The ease of filtration is same. So obviously it is same because they are operating at different pressures. PA is not equal to PB, but PA power 0.8 is equal to PB power 0.3. Because they are saying here that the ease of filtration is same. Otherwise this equation is also not correct. I can't do this. Since they are telling me this, I'm equating like this, and for a numerical view of things, I'm solving for the second case where the pressure is doubled, and I find that the resistance is more in case of A and less in case of B. Right? Therefore, B will filter faster than A. Clear? Agreeable? Okay. Take 2 minutes to answer this. It takes 15 minutes to filter a slurry of 1000 liters using a filter of 2 meter square area and a pressure of 10 bar. How long will it take to filter 10 meter cube of same slurry with a filter area of 4 meter square and 15 bar pressure? Assume incompressible cake and resistance offered by cloth is 0. So we are not having any Rm is 0 and S is equal to 0. Right? So let's use the formula T is equal to V square mu into SC rho naught by 2a square into delta P. Right? Since they have not given us any information except for time, volume, and filter area, and pressure. Right? So this one's there, area is there, volume is there. All other components are not known. Right? So let's bring the useful variables including this constant we are going to throw out. So T into a square delta P, T into a square delta P divided by V square, right, is constant. So what can I do? How long will it take? So T2 is the question. So T2 into what is the area? Let's write the known and unknown for case 1 and 2. Case 1, sorry, Case 2. So case 1, you have time is equal to 50 minutes. Slurry volume is equal to 1000 liters. Since the next one is going to be in meter cube, I'm going to convert this as 1 meter cube. So volume is 1 meter cube. Filter of area is 2 meter square and pressure is 10 bar. Case 2, how long will it take to filter 10 meter cube of same slurry with a filter area of 4 meters square and 15 bar pressure. Here if you notice, the volume is also same, of the same slurry it says, correct? Then I don't have to worry about, oh yeah, I'm sorry, it's just about the quality of the volume, I mean slurry. The volume is still changing. Sorry about that. So into what is A2? 4 meter square. Since the units are the same, I don't think we need to worry. Let's just leave it there. 4 whole square into pressure 15 divided by volume square 10 square is equal to, what's first time, 50 into area square 2 square into pressure is 10 bar whole divided by 1 square. So this is as good as nothing. So we will have T into 16 into 15 is equal to 50 into 4 into 10, and I'm bringing this to the numerator into 100, right? T is equal to 50 into 4 into 1000 divided by 16 and 15. So it's giving me 8.33 minutes. Are you getting the same answer? Am I right? Okay, there's a decimal error there. Thousand liters is 1 meter cube, right? Thousand centimeter cube is 1 ml. Centimeter cube is 1000 ml equal to 1 liter. So 1 meter cube is 1 liter. Acha. So that's wrong. That's wrong. That's wrong. 1 centimeter cube is 1 ml, right? So 1000 centimeter cube is already 1000 ml. So this is already 1000 liters. So I am right, right? 1 meter cube is 1 liter, correct? 1000 liters. Oh my god. So have I made some decimal error here? Are you all getting my answer? Guys, are you there? You can reply in the chat because I don't seem to be hearing anybody speak. 50 into 4 into 10 into 100 divided by 240. Oops, my bad. I did not see my calculator properly. So there we have it, 833 minutes. Correct? 833 minutes. Yeah, there you have it. So our answer is 833 minutes. Question 7. A particle half the size of the original particle will settle 2 times faster, 2 times slower, 4 times faster, 4 times slower. So we are talking about settling here. What formula do we have for settling? V is equal to d by 18 mu, d square by 18 mu into rho solid minus rho liquid into Gc, since it's, we assume it is gravitational settling. So you have d square here and the velocity on this side. So v1 by v2 is equal to d1 square by d2 square, and d2 is half of d1, right? Is equal to d1 square by half of d1 the whole square. What does that give us? d1 square divided by 1 by 4 d1 square, because I'm squaring half here. That will go to the numerator as 4 d1 square by d1 square. I can cut these. v1 by v2 is equal to 4, which means v2 is 1 by 4th of v1. Agreed? This is the new velocity we are talking about. So it is 4 times slower, right? The bigger the particle, faster it will settle. Smaller the particle, slower it will settle. Correct? So the particle half the size is actually going to be slower. So that gives you only two options, 1 and 2. But since you have a square here, it is going to be 4 and not 2. Agreeable? Okay, let's go to question 8. If I use a bowl centrifuge to separate the solids from slurry, the throughput of the centrifuge for 2 centimeter diameter particles when compared to 1 centimeter diameter particles will be, again it's the same question. The throughput of the centrifuge is a function of the velocity as well as particle size. The velocity is again a function of particle size. So v2 by d1 the whole square. Correct? Now the question is for 2 centimeter diameter particles. Correct? So that is your v2. I'm sorry, d2. d2 is equal to 2 centimeter whole square. And how is v2 changing with respect to the initial case where when compared to 1 centimeter diameter? So d1 I'm taking it as 1 centimeter by v1. Correct? So you will follow the same process. v2 by v1 is equal to 4. Clear? Previously what I had done is I had mismatched v1 with d1's value and d2 with v1's value. So the first case is your throughput for 1 centimeter dia, where d1 is equal to 1 centimeter, and v2, how is it changing with respect to v1 when d2 is equal to 2 centimeters? So is it agreeable? Let me know in chat if you're confused. Okay, I'll take that as it's clear. So it goes up by a factor of 4 because V2 is 4 times V1, right? So it goes up by a factor of 4. A particle moving at a velocity of 5 centimeter per second has a Reynolds number of 5. If it is broken into half, what will be the Reynolds number? What is Reynolds number? dv rho by mu. And they have given you velocity is equal to 5 centimeters per second. Nre is equal to 5. So let's take Nre2 is equal to d2 v2 rho 2 by mu 2 divided by Nre1 v1 rho 1 by mu 1. So that would give us d2 v2 rho 2 by d1 v1 rho 1 into mu 1 by mu 2. Are we clear? Right now, there is no change in viscosity. A particle moving at a velocity of 5 cm per second has a Reynolds number of 5. If it is broken into half, there is only change in d. And we don't know about velocity still. Density is not changing. Viscosity is not changing. And what is the Reynolds number? And the velocity is, for the first case, Nre2 is what we need to know. Nre1 is 5. D2 is half of D1, right? 0.5 of D1 into V2 divided by, what was D1? D1 into, what's the velocity? 5 centimeters per second. To slash this out. So I'm going to assume the velocity does not change. I'm going to take this as 5 centimeters per second and slash this off, since there is no mention of uh, whether the other parameters change or not. In that case, what would NRET2 be? 2 is equal to 0.5 into 5. That is 5 5s are 25, 2.5. Right? First Reynolds number is 5. Reynolds number 2 is 2.5. Let's check. Yeah, it fits within the range. Since they had not mentioned anything about the velocity, viscosity, or density changing, I'm assuming everything as constant. So Nre is equal to dv rho by mu, and all of these are constants. So Nre1 is equal to d1, Nre2 d2. And d2 was half of d1. So d1 by 1 by 2 d2 or d1 is equal to Nre1 by Nre2. So you will have Nre1 is equal to, you get this in the numerator, 2 Nre2, and this is 5. 5 by 2 is Nre2 is equal to 2.5. Clear? Going ahead. In order to measure the pressure drop through packed bed, we can use Newton's law, law of settling, Stokes' law, none of the above. So I'll just directly display the answer because there's nothing to explain here. Okay.